When the Cascadia subduction zone last ruptured on the night of January 26, 1700, the Pacific Northwest coastline dropped by several feet in a matter of minutes. Entire forests of cedar trees were plunged into salt water so suddenly that their dead bleached trunks are still standing today, more than 3 centuries later. Scientists have spent decades warning that this fault will rupture again in an earthquake capable of reaching magnitude 9.0. Now, new research examining exactly what happens to the land itself during that kind of rupture has confirmed something even more concerning than the shaking alone. When the big one hits, huge stretches of the Pacific Northwest coast won't just shake, they'll sink permanently by feet in some places, instantly expanding the flood zone across communities that have never planned for it. This is what scientists just confirmed about Cascadia's big one, and why the danger extends far beyond the earthquake itself. Let's be precise before we go further, because this deserves careful, accurate treatment. This isn't a claim that an earthquake is imminent on a specific date. What we're going to walk through is the actual mechanism behind the Cascadia subduction zone, the historical evidence proving it has ruptured catastrophically before, and the new research confirming a secondary danger that dramatically expands the disaster's real-world footprint. Start with the fault itself, because most Americans have never heard of it despite it representing one of the most dangerous seismic threats in North America. The Cascadia subduction zone stretches roughly 700 miles along the Pacific coast, from Northern California up through Oregon and Washington and into British Columbia. Unlike California's San Andreas Fault, where 2 plates grind horizontally past each other, Cascadia is a subduction zone, where the Juan de Fuca plate is slowly diving beneath the much larger North American plate. Now understand why that specific geometry makes this fault so uniquely dangerous. As the Juan de Fuca plate attempts to slide beneath North America, friction locks the 2 plates together rather than letting them slip smoothly. That locking allows enormous strain to build up over centuries, strain that eventually releases all at once in a rupture capable of producing some of the most powerful earthquakes on the planet, in the magnitude 8.0 to 9.0 range. Read that again, slowly. Not a regional earthquake. A megathrust event in the same category as the earthquakes that produced the catastrophic 2004 Indian Ocean tsunami and the 2011 Tohoku earthquake and tsunami in Japan. Here's where the historical evidence becomes genuinely chilling. Scientists have reconstructed the January 1700 Cascadia earthquake with remarkable precision, not through written American records, since no European settlers were present to document it, but by cross-referencing geological evidence along the Pacific Northwest coast with meticulously kept written records from Japan describing an unexplained tsunami that struck the Japanese coast with no local earthquake to account for it. That cross-referencing allowed researchers to pinpoint the Cascadia rupture's timing down to the specific night and to confirm it as a full-margin rupture, meaning the entire 700-mile fault broke at once, rather than in smaller, separate segments. Geological trenching along the Pacific Northwest coast has since identified evidence of multiple major Cascadia ruptures stretching back thousands of years, with recurrence intervals scientists estimate at roughly every 200 to 500 years. Indigenous oral histories from coastal tribes throughout the Pacific Northwest, passed down for generations before written records existed in the region, describe violent shaking followed by massive waves in ways that closely match the geological evidence scientists later uncovered independently. Researchers now treat these oral traditions as a genuinely valuable historical record in their own right, offering an additional line of confirmation alongside the tree ring dating, sediment layers, and Japanese tsunami records used to reconstruct the event. Let that land for a second. It has now been over 320 years since the last full-margin rupture, placing the fault well within, and arguably past the midpoint of, its estimated historical recurrence window. But here's what genuinely new research has confirmed, and why it's reshaping how scientists and emergency planners think about this disaster's actual footprint. A rupture along the Cascadia subduction zone doesn't just produce violent shaking and a massive tsunami. It also causes the coastline itself to suddenly and permanently drop in elevation, a phenomenon called coseismic subsidence. Now understand the mechanism behind that sinking. During the centuries, the 2 plates remain locked together. The overriding North American plate actually gets dragged downward and compressed by the friction, while also being pushed slightly upward and outward at certain points along the margin. When the fault finally ruptures and the plates slip past each other suddenly, that stored deformation releases all at once, and the ground that had been artificially compressed springs back, in some areas snapping downward rather than upward, dropping the coastline's elevation permanently and instantly. This same basic mechanism has been directly observed and measured during other major subduction zone earthquakes around the world in recent decades, including significant coastal subsidence documented after Japan's 2011 Tohoku earthquake and Chile's massive 2010 Mall earthquake. Those real-world observations gave researchers modeling Cascadia's potential rupture a solid, empirically grounded basis for their subsidence predictions, rather than relying purely on theoretical calculations. Recent detailed modeling research examining this subsidence effect found that some coastal areas across Oregon, Washington, and Northern California could drop by several feet in a matter of minutes during a full-margin Cascadia rupture, with the most severe subsidence concentrated in specific low-lying coastal communities and estuaries. Read that again slowly. Not gradual sea level rise playing out over decades. An instantaneous drop in land elevation of several feet in some locations, happening within the same few minutes as the earthquake shaking itself. Now here's why researchers describe this as making the overall disaster meaningfully worse than previous risk models accounted for. That sudden elevation drop doesn't just create new low-lying land, it permanently and dramatically expands the area vulnerable to the tsunami that follows the earthquake within minutes and to chronic flooding for years afterward, since the land literally sits lower relative to sea level than it did before the earthquake struck. To understand why that combination proves so dangerous, you have to understand the timeline involved. A Cascadia megathrust earthquake would produce a tsunami capable of reaching the coastline in as little as 15 to 20 minutes in the areas closest to the fault, leaving residents very little time to evacuate under the best of circumstances. Layering sudden coastal subsidence directly beneath that same short evacuation window means the tsunami's floodwaters would surge into areas that, just minutes earlier, sat at a meaningfully higher, safer elevation. Coastal towns built around estuaries and low-lying river mouths face the most severe version of this compounding risk since these areas already sit close to sea level, and the specific geological modeling shows some of these locations experiencing the most pronounced subsidence of anywhere along the entire fault margin. Communities like these often developed around historically productive fishing and shipping industries precisely because their low-lying sheltered geography made them ideal harbors, the same geographic qualities that now place them squarely in the highest. Risk category once both subsidence and tsunami inundation are factored into a single combined hazard assessment. Local economies built over generations around that same waterfront geography now face a genuinely difficult long-term planning question about how to balance economic reliance on the coast against a measurably expanding flood risk. If you've made it this far, you're clearly someone who wants to understand the real science behind this risk instead of just another dramatic headline. That's exactly the kind of viewer this channel is built for. So go ahead and subscribe if you want more deep dives like this one. Now let's be exactly as careful as the scientists studying this are, because that precision matters. Researchers cannot predict the exact date of the next Cascadia rupture. Earthquake prediction in that precise sense remains beyond current scientific capability for any fault system, including this one, no matter how well understood the recurrence pattern becomes. What this new subsidence research does confirm, with much greater specificity than previous modeling allowed, is exactly how much additional land and how many additional communities fall within the expanded flood risk zone once coastal subsidence is properly factored in alongside the tsunami itself. That's a meaningful upgrade in scientific understanding, even without any change to the underlying uncertainty about timing. That distinction matters enormously for emergency planning. Tsunami evacuation maps built without accounting for co-seismic subsidence may significantly understate the true area at risk, potentially leaving people just outside a previously mapped danger zone, unaware that the ground beneath them could sink low enough to bring the tsunami directly to their doorstep. So what does this actually mean for the millions of people living across the Pacific Northwest coastal region today? It means tsunami evacuation planning needs updating in communities where previous models didn't fully account for this subsidence effect. And emergency managers across Oregon, Washington, and Northern California have already begun incorporating this newer research into revised hazard maps. So what can you actually do with this information? Start by checking your specific address against your state's most recently updated tsunami evacuation zone maps, rather than relying on older maps or general assumptions about your area's elevation, since this newer subsidence research may have shifted the boundaries in your specific community. Know your evacuation route on foot, not just by car, since roads may become damaged or congested immediately after a major earthquake, and tsunami evacuation in the most vulnerable coastal zones requires moving to higher ground within minutes, rather than the hours available during most other coastal flooding scenarios. Practice that walking route in advance, ideally timing yourself, since official guidance in many Cascadia coastal communities specifically emphasizes reaching designated high ground within the 15 to 20 minute window before tsunami waves are expected to arrive in the areas closest to the fault. Knowing exactly how long your specific route takes, rather than assuming, can make the difference between reaching safety and running out of time. If you live in a coastal estuary community specifically, understand that these areas face the compounded risk this research highlights most directly, and treat your personal evacuation planning with the seriousness that specific vulnerability deserves, rather than assuming general coastal preparedness applies equally everywhere. And here's the step people consistently underestimate. Participate in Cascadia-specific earthquake and tsunami drills when your community offers them, since the muscle memory built through practiced evacuation is precisely what determines survival odds. During an event where minutes, not hours, separate safety from catastrophe. Large-scale regional drills, sometimes involving thousands of participants across multiple coastal counties simultaneously, have become increasingly common in recent years, specifically because emergency planners recognize that reading about an evacuation route is fundamentally different from physically walking it under simulated time pressure. Taking these drills seriously, even when they feel like an inconvenience on an otherwise ordinary day, is exactly the kind of preparation that translates into real practiced instinct if the actual event ever arrives. Before you go, let us know in the comments if you live along the Pacific Northwest coast and whether you'd heard about this subsidence research before today, because it's reshaping evacuation planning in real time. And if you want to keep tracking how this research continues to develop, stay subscribed, because we'll be following it closely as new studies and updated hazard maps continue to come out. Let's close where we started. A coastline that dropped several feet in minutes back in 1700, remembered today only through ghost forests of dead cedar trees standing in salt water. Scientists just confirmed it will happen again, and this time they know exactly how much of the map it's going to redraw. That's the real weight of this new research, and it's worth carrying with you well beyond a single headline. The big one was never just a story about violent shaking. It's a story about an entire coastline preparing in real time for the ground itself to fundamentally change shape. And the communities paying closest attention to that distinction are the ones most likely to come through it safely.